Use proof by induction to prove that 1 plus I to the power 4n is equal to negative 1 to the n multiplied by 2 to the power 2n. So let's consider the n equals 1 case. The left-hand side would be equal to 1 plus I to the power 4. Now we can work that out on the calculator, or we could work it out manually, but working it out manually is not that easy. I'm still in complex mode, so I can do 1 plus, and the I that I need is here. So put that to the power 4, and that's negative 4. And then the right hand side would be negative 1 to the 1 multiplied by 2 squared, which is also negative 4. So it's true for n equals 1. Now we'll assume for n equals k. So we're saying that 1 plus I to the 4k equals negative 1 to the k 2 to the 2k. We now want to consider the next case. So we want 1 plus I to the 4k plus 1. So that's 1 plus I to the 4k plus 4, which we could write as 1 plus I to the 4k, 1 plus I to the 4. So 1 plus I to the 4k, 1 plus I to the 4 is equal to negative 1 to the k, 2 to the 2k, 1 plus I to the 4. And the whole idea is that we've assumed this is true, and all I've done is multiply both sides by the same thing. So this must be true. So this one is 1 plus I to the 4k plus 1, and that's equal to negative 1 to the k multiplied by 2 to the 2k, and we know from up here that this was negative 4. So that's going to be negative 1 to the k multiplied by negative 1 multiplied by 2 to the 2k multiplied by 4. So all I've done is split the negative 4 into 4 and negative 1. So that's negative 1 to the k multiplied by negative 1 to the 1 multiplied by 2 to the 2k multiplied by 2 squared. So that's negative 1 to the k plus 1 multiplied by 2 to the 2k plus 2, which we can write as negative 1 to the k plus 1, 2 to the 2k plus 1. And then we can see that we have this with the k's replaced by k plus 1's. And then all we need is a closing statement. Use proof by contradiction to prove that root 10 is irrational. Now, there's a couple of different ways of going about the actual algebra, but we'd start the same way whatever we do. So let's assume that root 10 is equal to a over b, where a and b are both natural numbers, and a and b have no common factors other than 1. So what we're saying is this is a fully simplified fraction. Now, one way we can go from there is to start by writing b root 10 equals a, and then 10b squared is equal to a squared. So a squared is a multiple of 10, and that can only happen if a is a multiple of 10. So we can say that a is equal to 10c. Then we can say that 10b squared is equal to 10c all squared. So 10b squared is 100c squared. So b squared is 10c squared. We should say here that c, of course, is a natural number. So b squared is a multiple of 10. Implies b is a multiple of 10. And at that point we have a contradiction, because we said up here there were no common factors, but now we can see there's a common factor of 10. And so all we need there is a closing statement. Alternatively, from here you could go about the algebra differently. You can say that a squared is even, and that means that a is even. And then you can say, well, b cannot be even because a and b would then have a common factor of 2. If a is even, then a is equal to 2c, where c belongs to the natural numbers, which means that a squared is equal to 4c squared. So we then have 10b squared is equal to 4c squared, which would give me 5b squared is equal to 2c squared. So b squared cannot be odd, which means that b cannot be odd. So what we have is a situation where b cannot be even and b cannot be odd. We know that a is definitely even because 10 times anything is going to be an even number. And therefore, none of the cases work. And that's another contradiction. So you can either do it this way, or you can do it this way.